We're glad to have you here for a few days to lecture genetic singularities of free surface flows.
Oh,
Yes.
Thanks very much. So, thanks very much, Keith, for the kind introduction. Today, I want to talk a little bit about surprising universality that exists between singularities observed in very different systems, although most of my examples will be taken from free surface, some kind of free surface evolution. And what I'm going to present here is rather more the idea of a research program rather than finished results. I just got a research grant to carry out some of this work in greater detail. So I would welcome your suggestions greatly. What would be the best way to proceed?
spend money.
So here's one example that has interested me for a very long time, and where Keith has made a seminal contribution. But I'm showing you here some experiments where you have a very viscous fluid, the motion in which is governed by what's known as the Stokes equation, and it's being forced by a cylinder that's rotating. And what's observed experimentally is the free surface that exists between the fluid and the air, and you see that the free surface is forced into a very sharp cup. That is a free surface feature that ends in a point where you've got at least almost parallel tangents as you approach the tip from either side. And as you increase the driving, this tip becomes ever sharper, and the dependence of the radius of curvature as function of capillary number is predicted to be an exponential, which comes out from Keith's calculation in a particular case, but whose general trend was explained beautifully by John Hinch, who's sitting there. And it can be explained by the particulars of the of the Stokes equation, namely what kind of velocity field would be generated by such a sharp tip.
I think you just have to remind the audience what the capillary number is.
Oh, sorry. The capillary number is a dimensionless constant that measures the relative strength of viscous forces, which try to deform the free surface in a singular shape, and surface tension, which tries to smoothen the surface. And the surprising result here is that the smoothing effect of the surface tension is rather weak. That is, if you drive up this ratio, the curvature goes up exponentially very quickly. And here's one reason why these structures are important. Imagine you want to beat an egg, and of course you do it by mixing two different phases, by letting air enter into the viscous phase of the egg. And the idea is that you start with a singular structure and has a rather high radius, rather small radius of curvature here, and the singular structure serves as a seed for a secondary structure, namely a sheet of air to enter the flow.
Yes.
Obviously, if the surface is smooth, it's almost impossible for another phase to enter. Yes?
So what's the singular structure on the picture? I don't see it, on the egg.
I don't see it either. I don't see it either. Will show other pictures where you can see more of the singular.
But is it horizontal or vertical? I mean, the
it's here. Well, here's a little bit of a singular
the
structure.
picture.
It's all over the place. And but what I was just about to say is that the idea would be to, or hope would be, to understand the statistics of these singular structures under some complicated or random forcing, because that's what you would need to get at least a statistical handle on the likelihood or distribution of these events on the surface. So here's a slide that illustrates the analogy of this cusp to other systems. So here's another example of this viscous cusp. This is a rather nice experiment, which I recommend to do in your kitchen. So you take some olive oil and pour it into a beaker. So there will be a jet of olive oil entering the fluid here. It's not shown because the picture is cut off here. And the jet entering the bath deforms the free surface into the singular structure, which ends at the point here. You don't see the other half of the cusp because it's going right up here to join up with the jet. But there's this cusp buried in here, and if you increase, so you see this little silvery structure that ends in a point, and if you increase the height of fall a little bit more, that is, if you drive this system even harder, and then this cusp structure bifurcates, and suddenly you've got a sliver of air that shoots down into the viscous liquid, and soon after, your beaker is full of air. Here's another structure where a cusp has been observed, namely a caustic that's produced by the reflection of light from the walls of this cup. And the caustic is this bright line where the light intensity amplifies, and it again has this cusp structure. And like any singular structure, it is characterized by a scaling law. Now you can measure the width of this cusp as function of the distance from the apex, and that will be associated with a particular scaling exponent, and this scaling exponent is 3/2. So if you measure the width of this cusp here or the width of this cusp here, then its width goes to 0 like r to the 3/2 in both these cases. And we will see that, and actually its analogy goes beyond the scaling exponent. It's actually the complete structure of the singularities in both cases are related.
Is the location of the apex always unique?
No, if you turn your cup, then it moves. Then it moves around. But the leading order, these are.
I meant in this picture. I meant vertically. I understand that if you go to a different room and your light shines from a different side, then you'll be in a different spot.
Yes.
But you see, if you have a point where two tangents coincide, and you can always extend this by arbitrary lengths of line.
Mm-hmm.
Is the location of the cusp something uniquely defined? Is that, as you go along, is that the very point where the two tangents first?
Yeah, it's related to the radius of it's related to the radius of curvature of the cusp wall. So it's where, if you have rays coming here, it's where these rays
The
will
way to
first
say
focus.
it is not that the two tangents are the same, it's that the tangent reverses direction. That's a point, that happens at a point.
The issue is what defines the cusp.
Which is the
I
same.
mean,
as
these
mine.
things are coming in like this, and then it stops. But our
But I'll discuss the.
This is a classical curve anyway.
Change the
This is
radius
a
of
network
curvature
Mm.
in the section.
Tilt the white surfaces.
We weren't allowed to do that in the cup.
I think it will become clearer when I discuss this phenomenon. Here's another cuspy or singular structure. Remarkably, you can find cusps not only on the surface of viscous flow, but there are also solutions, cuspy solutions to potential flow. So this is a turbulent flow where you see a complicated lines of so-called Howell Peregrine like to call scars. And again, that is something you like to characterize, at least statistically. For example, if you will look at light scattering from a free surface underneath of which you have turbulence, you would like to understand the spectrum of the scattered light. And so you would have to understand statistics of all of these near singularities on the surface. Here's another famous example where you have the formation of such a cusp singularity in time. So this is Healy-Shaw flow without surface tension. Surface tension will round this cusp here. So you start with this blob and you extract fluid, and at a critical time, the initially smooth surface will deform into something that's cuspy. And again, the scaling exponent here is the same. It's 3/2. So let me just discuss the cusp structure first from the point of view of fluid mechanics, just to give you a feel of what arduous calculations are needed to even make modest progress on this problem. So here I'm only going to derive the outer scaling structure, that is this 3/2 exponent for this particular case. And the idea is the following. The idea is that if you have a cusp structure that is to surfaces which are asymptotically parallel, from a coarse-grained perspective, you can treat the cusp as a cut in the plane. And now what you want to do is you want to solve the equations of fluid motion, that is the Stokes equation, in this domain here, where here is the cusp tip, and you have boundary conditions of no stress along this line, because in this calculation I'm neglecting surface tension. It's a free surface. And you can find out what these solutions are by performing a local expansion of the equation. So the equation happens to be the bi-Laplacian, where psi is known as the stream function, and it's related to the actual velocities in this way here. And I'm looking for similarity solutions to the equations of motion. So I write psi equals r to the alpha times some angular dependence whose coefficients are to be determined. And I impose my boundary conditions. And after a calculation, and that's a bit more involved because you have to eliminate the pressure, but it's a reasonably complicated calculation, but straightforward. You get the following result. As usual, you actually get a sequence of eigenvalues. Okay. So the lowest order eigenvalue corresponds to alpha equals 1. which is expected because there must be a solution corresponding to a uniform flow in the y direction, in which case the flow doesn't even see the cusp. So this solution must exist. The flow simply glides along this cusp in this direction. And the next exponent is alpha equals 3/2, and it has this angular dependence where the coefficient A is undetermined because it's a linear problem. Possibly be determined.
What's the operator you're computing the eigenvalues of? I kind of missed that.
By Laplacian.
The Laplacian. Okay, thank you. Yeah.
Okay. Consistent with these boundary conditions. And the next exponent would be 2, and then 5/2. But the idea is these make contributions of lower order as r goes to 0. Now, we can, once we know psi, we can work out the flow. And once we know the flow, we can work out what free surface shape this corresponds to, because the free surface must be a streamline of the flow.
So you're working in a quadrant, is that right? You've changed coordinates so it's a quadrant. It's the positive x, positive y quadrant. I'm just trying to figure out why you get 3/2 powers as opposed to other fractional powers. What's the domain you're solving the Laplace equation?
In the whole, in the plane for the cut. And yeah, you also get 1/2, but that leads to non-integrable stress. So that's why you select the sequence of exponents, 1, 3/2, and so forth.
It's just because it's a non-standard singularity of the Laplacian that he's worried about, but it's because you cut the plane. You don't have just a singular point.
Of course, the fact that it's cut here is crucial.
Yeah, that's just where the cut was. It's just a single cut, actually.
Yeah, just a cut here, from the origin to infinity.
Is this incompressible flow?
Yeah.
So why do you need the bi-Laplacian? The Laplacian of psi should be 0. Or am I wrong here?
No, it's Stokes. It's viscous flow. In potential flow, indeed, you would have the Laplacian of psi, and in Stokes flow, you have the bi-Laplacian. It's actually the exact same calculation you use to calculate the so-called stress intensity factors in elasticity, because in 2D, elasticity is governed by the same equation. In elasticity, this would be the Airy function, and you do precisely the same calculation to calculate what's known as the different modes of stress distribution, and what's known as the stress intensity factors, and they're governed by the exact same exponents. Okay, so I here I've simply written down the corresponding velocity field in Cartesian coordinates, and now it's a rather simple calculation saying that the free surface must be a streamline of the flow, so dh dy goes like y to the 1/2. So lo and behold, h goes like y to the 3/2. So you might think, and I certainly thought until recently, that this is something very specific to the viscous flow problem. We use the properties of viscous flow in a very specific fashion to arrive at this particular exponent. But the question is whether there perhaps is something else underlying. So I asked myself the question, what happens if you simply have a line? So you forget that the free surface motion is governed by a particular equation. You simply ask yourself, you have a line that's smooth, and you deform it in some smooth fashion such that it self-intersects. And now you open this loop, and obviously as the loop opens, the line must have some singular structure, and you ask yourself, what is the singular structure that results from this operation? So let me just give you a feel for the calculation I've done. So I imagine I have a curve that's parameterized by some parameter phi. And so this is the lowest order expansion in phi. Of course, I can do a rotation such that my curve is in this normal form. And now I'm interested in the situation that this becomes singular. That is, that A1 goes to 0, which means that if A1 is 0, I must do my expansion in phi to higher order. Okay, so there's a critical point here. A1 equals 0 at this particular place. So I have to continue the expansion to higher order. So this is the general form I will get. And by doing another rotation, you can eliminate this quadratic term here, and you end up with the universal form I've given here. So this I call universal unfolding. So you can imagine you start with a curve corresponding to epsilon equals 0. Now you ask yourself, what happens to the curve if you deform it smoothly? And the statement is that locally, this singular shape will deform into a curve that has this scaling structure, where epsilon greater than 0 corresponds to this smooth curve, and epsilon smaller than 0 corresponds to this self-intersection. So now let me come to the calculation done by Zhong and Moffat about 20 years ago. So they solved this cuspy problem in a very particular flow geometry where you've got a particular kind of singularity, a double vortex, below a free surface, which is infinitely extended. And they found an exact solution to these equations. That is a solution valid everywhere, but they also analyzed the resulting shape close to this tip. And the result of this calculation, if you, here's again the singular, this dependence of the radius of curvature on the capillary number. And if you analyze the solution, you find that it has this scaling structure here with scaling functions where epsilon is essentially the small parameter, that is the radius of curvature. You should think of R as epsilon. And X and Y are these universal scaling functions. And so you will notice that the entire scaling form you find in this particular problem is precisely the one I found by generic deformation of a curve. So this I find a rather shocking result, because there's no bias in this calculation. I've forgotten completely about the underlying physics. Yet not only the characteristic scaling exponent of 3/2, the entire scaling form of the singularity is reproduced by this simple deformation idea. As usual, the only thing you're not able to predict is the actual value of this parameter epsilon. To do this, you have to do the actual calculation. So this geometrical idea, of course, does not explain this exponential dependence of the radius of curvature on parameters. Okay. So at this point, this is an observation. I haven't really shown that that this must be so. I just wanted to sketch what would be required to do that. You would first have to take the underlying equations of motion, for example, the Stokes equation in two dimensions. You would have to establish that the boundary is given as a smooth function of some parameters, which you can find out. Then knowing that there is a singularity, that is a cusp at which x with respect to the parameter is 0. Once I know that all of these dependencies on the parameters are smooth, I could then use the unfolding I've given in the previous slide to actually deduce that the scaling structure had to have this particular cusp form. Let me give you another, very simple example where this program could be carried out very easily. Of course, there are many examples of singularities like that. Just imagine that you have a circle which you're rolling on a surface, and you place a point anywhere on this circle, and this will produce some curve, and you ask yourself, what is the curve this is producing? Of course, if this point here is on the boundary, then as this point hits the boundary, it reverses direction, so it makes this, so you get a curve that's like that has a cusp. But since you know that the shape of this curve here must be a smooth function of the position of the point I've chosen, I actually know that if I move this point inwards to obtain a smooth curve, the shape I'm getting must have precisely the scaling structure I showed you, and you can indeed demonstrate that in this particular case.
But the scaling, so you're assuming some low order terms don't vanish, right?
Yeah, and there can be high order terms, higher order phenomena, which I'm going to present now. Because in optics, it so happens that this the first order, the cubic correction I've introduced vanishes, and you have to go to next order to capture the singularities you're interested in.
You must be assuming, though, that whatever you're doing, they satisfy some finite order differential equation, because obviously they're smooth functions that have infinite vanishing Taylor series that look cusp-like.
Yeah.
You're using like the Laplace equation or something. There's some equation that's governing all of your examples to get this.
Yeah, and in the case of, say, Stokes equations, technically the most promising approach to actually show something like that is to use complex dynamics. So that's also the technique Keith used to solve the problem. To actually, there are many examples where you can transform Stokes flow into a dynamical system where the boundary is characterized by a finite number of parameters, and you write down ODEs for these parameters. And then you have to analyze the dynamics in near points where singularities of the mapping hit the boundary. And local expansions of this dynamics as the singularities hit the boundary will correspond to exactly to the expansion around the cuspy curve I showed you.
Actually, the underlying dynamic equations play almost no role, actually, because all these singularities and these expansions that you make, whether you know you've got the right ones, are determined by them being stable under diffeomorphism.
Mm-hmm.
And that's something that is very weakly dependent on the equations that they satisfy. I mean, you need Taylor expansion, you need smoothness, but that's all you need. I mean, the calculation that you actually did, I mean, when you say you manipulate these functions, you don't make much use of the underlying...
No. But in hydrodynamic...
I mean, they are there.
In case of hydrodynamics, it's not so clear this is actually true, and there could be symmetries, there could be cancellations that actually tells you that
if you build in symmetries, then you've got what the equivariant singularity, which was studied in the 1970s by Ian Stewart and others. So you can build symmetry in if you have it.
Mm-hmm.
But you've got to know it.
Yeah. And it's not so easy to see what the symmetries are, which are formulated in the equations, what they are in the language of these curves.
So you raised a very interesting word there, stability. There's a stability to the geometric mappings that you might like to think about. However, there is also dynamical stability that we could set up a solution. It's just not stable in time.
That's right. That's a separate thing.
It's never a realizable.
It's a very important distinction. Yes.
Yeah. And in fact, in these cusp singularities you find in potential flow seem to suffer from this problem. I'm going to mention that briefly if I progress a little bit. So you can ask yourself. Let me just ask this very naive question, which you can also ask in the Stokes flow case. So where does the cusp come from in the Stokes flow case? It comes from the downward streaming induced by the double vortex. Now imagine I reverse the flow, so things go up. Then there will be no cusp. And so you ask yourself, if now I have a driving and I have a little knob, and imagine surface tension is 0. So whenever there is the slightest excuse, there will be a singularity. I can ask myself, as I turn the knob, where does the singularity first occur? And I claim it first occurs through another bifurcation, which I will show you now using the example of wave fronts. But my claim is it actually happens in the same way in the Stokes case. This is caustics, and I'm going to look at the phenomenon of caustics from a rather unusual way. I'm going to look at caustics from the point of view of wavefronts, simply because that's the closest analogy to my physical free surfaces I have in fluid mechanics. What's the dynamical equation that's governing a wavefront? It's called the iconal equation. It simply means that if phi labels a ray, then any point here will move at a constant speed in the normal direction. And it's easy to see that this equation is actually quite simple because the normal actually doesn't depend on time. Once you are an array, it will continue to move in the same direction. So the equation is actually very simple. It's this equation which you can integrate directly, and I'm going to reformulate it slightly differently. Sorry, I should have made a diagram here. So h of phi is the initial shape of my wave front, and x and y is the evolution of this wave front under this dynamic. So for t equals 0, this curve here is this initial wave front h of x, y equals h of x. And now you ask yourself where this wavefront becomes singular, and it develops singularities of the form dx d phi equals 0, which means that different rays coincide, neighboring rays coincide, so the light is amplified, so dx d phi equals 0 is the condition for a caustic, to lie on a caustic, from the point of view of the wave front. So let us analyze these points here. If you are at any point on your initial wave front, and if your shape is convex, as illustrated in this diagram, you will always form a singularity. And the time at which you form a singularity will simply be given by the local curvature of the initial wavefront. So actually, from each point along the wavefront, there emanates a ray which will eventually become singular. And so you have to look at the place where along the entire wavefront the singularity first occurs, and that corresponds to the maximum of the curvature. That's the point where you have optimal focusing. So you have to expand, say, around this point where you have the greatest curvature. So if you do that, you can do that simply by expanding my initial wavefront around this point into an arbitrary power series. Higher order terms don't matter. So you take this and you expand around this point t0 where the singularity first occurs. And if you do this expansion, you end up with a similarity form. And the interesting point is that this is not the cusp I've been showing you earlier. You have to go to higher order here and take into account terms of fourth order here. And so the condition for this, now I have to write down where does this shape here become singular, and the answer is for any given point sigma, or let me say for any point t prime, there is a point parameterized by sigma along the wavefront where there is a singularity, where there is a tip. Now, what is the caustic? The caustic is the locus of all the points traced out by this condition. So what I do is I let time run. This gives me a sequence of sigmas. I plug that back into this equation, and this will trace out my caustic. And then finally, this is the answer. These are the points that lie on the caustic, obtained in that way. And then the caustic is a cusp that has this characteristic 3/2 exponent. But what do the wavefronts look like? And I hope this answers your question. So what I've been doing, so this is the initial wavefront I've started from. This is where focusing first occurs. But at later times, all the wavefronts are singular. And they're singular in this peculiar way, namely they form two cusps. They have not one cusp, but two cusps. And these two cusps are born at this out of a bifurcation at this point here, which is a higher order version of the expansion I've just shown you. And the tips of these cusps trace out the caustic, which has this characteristic which has this characteristic form. I said there's this point where suddenly two cusps are born. So you can ask yourself, where is the viscous cusp Heath described born, and one could look at the viscous equations, but actually the same question was investigated a long time ago by Bertram Hopkinson, who used to be an engineer here in Cambridge. He developed something like the Hopkinson bar to measure pressures, I believe. But he also wrote a beautiful theoretical paper on singularities of potential of the free surface potential flow. And he looked at this model system that you have a two-dimensional drop with singularities inside. And if you place a double vortex, as Keith did, inside this drop, then you get two cusps. You can have exactly the same structure. But Hopkinson must have asked himself, where does the cusp come from? He didn't, there is no abstract, there's no motivation. He just has pictures, but that's what he must have thought. So to this double vortex, he adds a single vortex. If you do that, then you find there is actually a point here where this swallowtail occurs, which I call the structure we've just seen in the example of wavefronts. So very close to this point, if you tune the single vortex to the right value, this is the point where this interface first becomes non-smooth, and then two cusps are born at the same time, and then they eventually wander to this position. And this is an example where you have a particular symmetry, because this singularity is of higher order. If you deform it, you actually have two free parameters. You have two free parameters by which you can deform this germ, the swallowtail germ. But in the context of potential flow, you're using only one of the parameters. That is, this cusp tip always remains sharp. If you have viscous flow, on the other hand, you can have this bifurcation, but these tips here become rounded, as they must if you introduce surface tension. And I think I have outlined this very briefly here. So you start out from a germ, you unfold it, you have a certain number of degrees of freedom called the codimension, and then you obtain this universal form. You start from a higher order singularity, which has this germ, you deform it, and now you have more degrees of freedom. There are two parameters, epsilon 1 and epsilon 2, you can play with, and in general, you get a structure like that. Where this is actually a self-intersecting shape for the viscous flow, you would like to tune it such that you get a smooth tip over here. So far I've described phenomena which are known from exact solutions, from analysis of particular equations. Can you actually make predictions using this idea? And this is where most of the work remains to be done. I just want to illustrate that you can make predictions. For example, if you take Stokes' flow and you go to higher dimensions, then you're lost. All the methods we have, that if you any of this insight, are bound to 2 dimensions. They don't work at all if you have higher dimensions. This idea here, on the other hand, is not really bound by dimension. it just becomes more complicated. And the idea is that you start from a cusp. You choose your coordinate system that XSS points in the direction of the cusp, and XT is then a vector that points in the direction normal to it, that is tangential to this cuspy surface. And then if you unfold the structure, you once more have two parameters, one parameter which controls the maximum curvature here, and another parameter which controls how this cusp structure opens up as you go in the normal direction. And so this structure would be an actual prediction on how a singular structure of the Stokes equation should behave in higher dimensions. And that's one of the things I plan to investigate, numerically perhaps, to verify that the singular structures are actually of this form.
So the cusp in 3D is a point still, it's a single point.
Yeah, that's the assumption that I expand around something that's actually uniform around the cusp that's uniform in one direction, and then I ask myself, if I perturb it smoothly, what are the possibilities?
Yeah, that singularity, is it, as you've illustrated, is it a point or is it a little bit distributed along a line?
This is plotted for finite epsilon 1, so that is actually distributed along a line. If you put epsilon 1 and epsilon 2 to 0, then it is a perfect point and it is uniform in this direction. And you have two parameters to open up this structure up.
Codimension 2, if you're in 3 dimensions, is the cusp edge. Codimension 3 would be points.
Mm-hmm.
So if you've got codimension 2, you're describing a cusp edge.
Yeah.
Yeah. So it's a line, not a point.
Right, but there's a parameter value where it's a point.
No, well, that's not right. Then it's not stable. But then you have the umbilicus, if you want to go further, or the swallowtail, depending on your co-rank. In other words, depending on how many of the underlying variables, which here you have x and y, how many of them are active and how many are passive. So that's different between co-rank and codimension. So if you've got codimension 2, the distinction is moot, and you just have the cusp edge. But if you've got codimension 3, you can have either the co-rank 1 singularity, which is swallowtail, or you can have the two umbilics, if you're speaking in the world of gradient maps. If you're not,
Exactly.
If you're not, then because other things can happen.
And that's the problem. Thanks for this remark. Of course, all of these structures are very reminiscent of the structures you find in catastrophe theory, where you're describing structures where you have a potential, and where the structure you are describing are the critical points of this potential. And in all of my examples, you don't have that. So that's why there is some work to do here, just to see how far you get without this assumption. But still, I think the guide to this endeavor should be just to look what kind of structures you have in catastrophe theory and try to understand whether you can make a link. It's just, as far as I know, no one has really applied catastrophe theory in any serious way to these say, viscous flow problems. Whereas I strongly believe the evidence is that there is a strong link.
Well, one direct application, which, as we've been speaking, I've just sent to you, is understanding in fluids how, if you have an incompressible but not irrotational flow, then let's say in 2 dimensions, then the singularities can be vortices or stagnation points, And how they can coalesce and separate as you change parameters is exactly catastrophe theory.
Yeah.
It was applied in the 1970s. We studied a rather complicated case. If you have 6 rollers,
Yeah, I know. Yeah.
then as you change the speeds of the rollers, these saddle points and stagnation points and vortices can interact and coalesce in a variety of ways, but they're all classified by one of the codimension 3 catastrophes. So there are examples.
Yeah.
You're speaking about others, and in that case, you definitely have a potential. It's a velocity potential. It's fairly elementary from the point of view of
Yeah.
mechanics.
Yeah.
But the examples you take are much more sophisticated. And as you say, there's work to be done, and you actually don't know whether the singularities are of the potential type. It's a guide, but they could be different.
There could be that, and that's what we hope to do in this
Singularities of
project.
smooth mappings are different from singularities of gradient mappings once you go beyond codimension 2.
Yeah. And this is was the end of my talk. Yeah, so you back out, the scaling response, which would be predictions to be verified, say, by a numerical simulation of a Stokes flow in 3 dimensions. Here's another potential type of singularity where you have 2 directions in which these derivatives vanish, and the question is if you can describe sort of budding phenomena of this type here. And here's another example that arises if you study a line in 3D. You can do the same thing. You assume you have an arbitrary, now the line is no longer in 2D, it's allowed to move around in 3D. You assume you have a point x phi, and then you can find your universal unfolding. This time it has codimension 2. There are 2 parameters, epsilon 1 and epsilon 2. If you have just another example where you have a particular symmetry, if you were to apply this to the singularities of cosmic strings, it turns out that not all of these possibilities are realized. There's a particular constraint. You only have singularities of the type epsilon 1 equals epsilon 2. Just as in potential flow, there were also just a particular, and in the example of wavefront motion, there was just one particular case that was actually realized. So in conclusion, singularities form generically. They often seem to be determined by very simple geometry, cost per swallowtail, or possibly even higher order objects. And so my goal would be to, without the benefit of having the potential to reach a more systematic classification, at least in 2D and 3D. One possible, as I mentioned, one possible analytical handle to make a closer connection to the actual physics would be to use the motion of singularities of complex mappings in the plane. Thanks very much.